How about now?
Yeah, we can see it. Go ahead.
Right. Good afternoon, ladies and gentlemen. The time is now 3:33, so we're gonna go ahead and get started. It's my pleasure to introduce our guest speaker today, Dr. Krister Shalm. So Dr. Shalm has done his Bachelor of Science in Engineering Physics at the Queen's University in Canada, and then he went on to do his PhD at the University of Toronto in experimental quantum optics under the tutelage of Ephraim Steinberg. In 2010 to 2012, he was at the Institute of Quantum Computing in Waterloo, Canada. Recently, he has made his home at the National Institute of Standards and Technology, but when he's not tinkering away in the lab, he's probably out swing dancing, so go check out his blog. And ladies and gentlemen, now, dancing physicist himself, Krister Shalm.
Thank you. I promise I won't make anybody dance during this talk. It'll be strictly physics, but you know, I'm looking forward to the vaccine rollout and being able to actually go out dancing, because it's been almost an entire year since that's been possible. But a lot of things have changed for folks. So I just wanted to, before I really begin talking about our work on quantum entanglement and using it to really study fundamental properties about randomness, I'd like to just say it's a pleasure to speak to the to LSU, because I feel like LSU over the years has been a real powerhouse in quantum information. There's a lot of strong connections. When I started my PhD, my initial work was actually heavily influenced by John Dowling's theories and work on Noon states and trying to build quantum metrology and quantum sensing. And more recently, Omar, who's now faculty at LSU, he did a postdoc here at NIST and was involved in some of these experiments and some of this work. And also this past year, I've had the pleasure of working with Elisa, and she's come on board and helped out with a number of some of the more theoretical aspects of this particular project. And just down the road from you folks at the University of New Orleans, there's a newer faculty member, Peter Bierhorst, and he did a lot of the theory behind this work that I'll be talking about today. So there's a lot of strong Louisiana connections. And so it's a pleasure to speak to you about some of this work. And before I really get into the meat of things, I'd like to spend a bit of time talking about Bell's theorem. That's really what we'll be talking mostly about today. And it's such a pivotal theorem in quantum mechanics. It really sits at this unique intersection of philosophy, quantum mechanics, and computer science. And that's where we get quantum foundations and quantum information, all kind of come out of Bell's theorem. They trace their origins there. And I'll talk, if you'll indulge me, I'd like to spend about half my talk really going through Bell's theorem. If you put 10 people in a room who are experts in quantum mechanics and Bell's theorem, you'll probably have about at least 15 different opinions on what it means. So I'm going to walk you through kind of what Bell's theorem means to me, and also how we're going to connect this to randomness generation. And then we'll talk about some of the experiments for the second half. So just to give you a brief overview, Bell's theorem came out in I think it was like 64 or 65, sometime around, early to mid 60s. It took about 50 years before we were able to do the full version of his experiment, what's called a loophole-free Bell test. It took about 50 years to develop the technology to carry this experiment out. And the first three were done in 2015. I was involved in the ones at NIST in Vienna. And then since then, there's also been two other experimental demonstrations as well and setups, one in Munich and one in Hefei in China. So the title of my talk really comes from this quote from Einstein. He said, "As I've said so many times, God doesn't play dice with the world." And I think he said this, or variants of it in a few different places. There's this wonderful book called the written by Max Born about his letters with Einstein. He published all his letters back and forth. And a lot of the great Einstein quotes about quantum mechanics come from this book. You know, it's where we get spooky actions, and also this quote about, you know, God not playing dice with the world. And it really stems from this idea, at least from classical thinking and Newtonian physics, and then through his general theory of relativity, that the world should be, in some sense, deterministic. That if you knew the position and momentum of everything in the world, you should be able to predict what's happening. And quantum mechanics was had this kind of element of fundamental randomness to it. And Einstein thought that there should be something that kind of went beyond that. And I think this idea of classical thinking, you know, it's, if you want to really think about or talk about or read about the history of some of these great debates between Einstein and Bohr, Howard Wiseman has this great article that I highly recommend everybody read. It goes into EPR and a number of other topics. So this is if you want some history reading, this is a great source for it. So this idea of classical intuition, I really love this. Well, I love a lot of what Laplace wrote, but he has this great little treatise on probabilities, this essay. And in it, he says, the curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. And so the idea was, we have to develop statistical methods, statistical mechanics, because we can't keep track of the position and momentum of, say, every gas molecule in a container. But that's the only reason we have to resort to that is because, you know, we were ignorant about those properties. But in principle, if we could track the position and momentum of every single particle, we could predict exactly everything that would happen, and we would know everything that happened in the past. And so this was the sort of gist of the kind of complaint against quantum mechanics, was that, sure, a photon hits a beam splitter and we don't know which way it's going to go, but that randomness, maybe that photon just has some extra properties that are hidden from us, and we have to rely on quantum mechanics, which is statistical in nature, to describe that. And so just as classical statistical mechanics has a deterministic underpinning, why doesn't quantum mechanics also have, which is a statistical theory, have some kind of deterministic underpinning and have these extra parameters of variables, which we sometimes call hidden variables? Well, John Bell came along, and with his theorem, this is his paraphrasing of it, he says, if a hidden variable theory is local, it will not agree with quantum mechanics. And if it agrees with quantum mechanics, it will not be local. This is what my theorem says. So we're going to go through a little bit about what that means. Local meaning that you can only influence your local environment. You can't send or correlate faster than the speed of light. So this brings us to the crux of the talk. If quantum mechanics says that, you know, the universe there is randomness in the universe, in other words, that God does play dice with the universe, what do those dice look like? And it's my contention that those dice look like a loophole-free Bell test, a test of Bell's inequalities. And I'm going to spend some time going through talking about why you might want to use this as a source of randomness, a loophole-free Bell test, and what are the problems with current random number generators. And then a little bit about how Bell's theorem works, some of the intuition behind it. So to start with, I need to define what randomness is. There are many different definitions, but my definition is just simply that randomness is unpredictability. Something is random if it couldn't be predicted in advance, and preferably by nothing in the universe. So nothing in the universe could have predicted what your next bit is going to come out of your random number generator. And so throughout history, until very recently, the last 100 years or so, the best random number generators we've had are a pair of dice. That is the best source of randomness that we've had. And generating large amounts of randomness, today we need randomness for things like cryptography, but when you started getting into the 40s and 50s and 60s, as you started to do larger and larger simulations, you needed random seeds for your simulations. And so the Rand Corporation actually published a book, which is just 100 million random digits. It's like 100 million, or sorry, it's not 100 million, it's a million random digits from 0 to 9, each of them, and it's just pages and pages. It also has this bonus feature of 100,000 normal deviates. This, as you might imagine, wasn't exactly a bestseller, but still very, very useful. Maybe if it had been 100,000 normal deviants, it might have done a little bit better. But this was an incredibly valuable resource and has a lot of historical importance as a record of how people really needed to generate randomness. Well, very recently, within the last month, there's been a paper published in Science of an ultra-fast random bit generator that now can put out about, in principle, could put out about 250 terabits of randomness per second. So 250 terabits is the sort of state of the art for randomness generation. So we've come a long way from throwing dice to writing books about randomness to kind of what the state of the art currently is. And so this random number generator and many of the random number generators that are in today are very good. And but all of the random number generators suffer from some in principle difficulties. And so, you know, we could even take what I consider to be a very good random number generator, and that is a beam splitter, a 50-50 beam splitter. You send a photon, and it has a 50% chance of going one direction, up or through, get reflected or get transmitted. And we can have two detectors on either side. And if you see a detection in one side, you see a 1, detection on another, you see a 0. This is using quantum mechanics, it's using randomness. And you can actually make a very good random number generator out of it. But there's a problem with this source of randomness and every other source of randomness that's in existence. And the first one is, how do you tell, if I just gave you the bits coming out of this, how do you verify that those bit strings are uniform? There are some tests you can perform, but there's no standardized way to do it. And you know, you can actually pass some tests and fail others. And so it's very tricky to really look at the uniformity of the string. And we'll go through an example of that in a bit later towards the end of the talk. The second real issue is, how can I tell that the process of the photon hitting the beam splitter is really random and there's not something else going on that I'm not taking into account? So for example, if you actually try to build one of these in the lab and just do the naive approach, you very quickly find out that you produced a very biased random number generator. And if I wanted to like hack this random number generator, well, there's a whole host of assumptions that go into building something like this. And the first is that beam splitter is actually a beam splitter. Now, sometimes when you try to make these beam splitters, what you end up with is the coatings that go into layering these, they can be off a little bit. And depending on the color of the light coming in, you can be more likely to reflect than transmit, or vice versa. So if I knew that, I could just play with the power grid, and the laser that's producing these photons, I could change its color by driving the power. And then I could direct and have a very good accurate idea of, you know, did it reflect to a 1 or did it transmit to a 0? And I can actually take control of the random number generator. Well, maybe you fix that problem, but it also turns out that these detectors tend to be very temperature sensitive. So just by measuring the temperature in the lab, if I knew what was going on outside, I could also actually very well predict what's happening. And so the problem is, it's how do you really know that the thing that's generating the randomness was truly random, and that there wasn't what we call in cryptography an extra side channel leaking up the information. So that's a huge problem. And the third big issue with any cryptographic system, not just randomness generation, is you have to have some level of physical security over your devices. So it doesn't matter how good your randomness generator is, but if the hard drive that's storing the bits at the end has been compromised by somebody else who swaps in another hard drive with pre-programmed bits, so you pay the janitor off to do this, you're completely compromised. Now, quantum mechanics and this Bell test, entanglement, we can actually address problems 1 and 2. It's the only known way that we have a solution for overcoming these first 2 problems. Unfortunately, this third problem, there is no physics solution or technological solution you can really throw at this to solve that. You always have to have some trust in the human operators at the end, or have access to the physical machines. So we can't solve problem number 3, but we can solve problems number 1 and 2, or at least address them in the best way possible with the Bell test. So I'm going to go through Bell's theorem and try to explain how it rules out hidden variables. And oftentimes, you could almost think of Bell's theorem as being really the first quantum protocol, this kind of game that he proposed, or this test. And there's lots of ways you can restate this particular test. I'm going to go through my particular favorite and just give you the intuition for what's happening. So forget photons and quantum mechanics. Let's just say that to start with, you have 2 people, Alice and Bob. These are the Alice and Bobs that we chose to use in our experiment. I didn't pick them. I came into the lab one day and somebody had posted up Alice from Dilbert and Bob Marley, I guess because it's Boulder. There might be connotations there, I don't know. So these are our Alice and Bob, and they come up to me and they say, Krister, we are psychic and we can prove it to you. You can do any test you want and we will show you that we're psychic. And so after thinking about it for a while, I come up with my first attempt to try and prove them not psychic. So I put them each in a room and I barricade it off so they can't talk to one another. And I give them each a piece of paper. One side of the piece of paper, there's a plus. The other side, there's a minus. And I've also got a light in each room. And so when the light goes off, that means that a trial is going to happen. And the reason I've got this light is because I don't want to be in the same room as them and kind of give away any information just by my facial expressions or what's happening. So basically, every single time they're going to, this light's going to go off and they're going to show me a plus or a minus. And I'm going to demand that whatever they show me, they remain correlated. So if Alice shows me a plus, Bob has to show me a plus. Alice shows me a minus, Bob has to show me a minus. And so we're going to play this game. And I'm going to see if they're truly psychic or not. So I run the game, and lo and behold, they win every single time. Should I believe that they're psychic? I usually ask this to a room full of people, but unfortunately, it's a little hard to do that right now, so I'll just tell you the answer. No, this is a terrible test because there's lots of ways they could have coordinated in advance. Maybe they just synchronized their watches beforehand because they knew the rules of the game. And every time a second hand was sitting on an even number on their watch, they gave a plus. And if it went to an odd number, they gave a minus, or maybe they memorized digits of pi. Or maybe they just agreed in advance that all they're going to do is show me plus no matter what. So every time I run the game, they just show me plus. And by the rules of the game I set up, they win. So this is not a very good test to see if they're psychic, because they could have shared some hidden information hidden from me that allowed them to exactly correlate their answers perfectly. And that hidden information is exactly what we mean by a hidden variable. It's whatever coordinating strategy that they might have come up with. All right, so I go away and I think about it a little bit more, and I'm going to come up with a different version 2 of this experiment. So what I'm going to do is now I'm going to add to Alice and Bob. They're each going to have 2 pieces of paper. Again, one side has a plus, the other has a minus. And now there's going to be 2 lights. And I'm going to have a little random number generator that's going to pick for Alice which of her lights is going to go off. And same thing for Bob, a random number generator that picks which light to go off for him. And the key here is Alice has no idea whether it's the left piece of paper or the right piece of paper that I'm asking Bob to respond to. He doesn't know which of the lights has gone off, and Alice doesn't know which light has gone off in Bob's room, and vice versa. And because it's a game, I'm going to give them a point every time they get the correct response, and a -1 for every incorrect response. And here are the rules of this new game. If Alice's outer light goes off, Bob's outer light goes off, they need to give me a correlated answer just like before, plus plus or minus minus. If Alice's outer and Bob's inner goes off, they need to give me a correlated answer. If Alice's inner and Bob's outer goes off, they need to give me a correlated answer. But if they both have their inner lights go off, they need to give me an anti-correlated answer. And so if they're truly psychic, right, then Alice will have some kind of notion about what Bob's setting is, and she'll know how to respond. And they can kind of coordinate the response if they're psychic. But if they've shared this kind of hidden strategy in advance, Alice can't know what Bob's setting is. And so she doesn't know if she needs to respond correlated or anti-correlated. And same thing with Bob. So if they're psychic, they win every single time. It doesn't matter what the settings are. They can always give me, you know, three of the times they'll give me a correlated response, and the other time they'll give me an anti-correlated response. They always win. So on average, their score is going to be 4. If I average up over the number of times I run the experiment, their score will be 4. However, if they have a hidden parameter or variable, then we'll see that their score can be at max 2. And so there are an infinite number of strategies that they could pick and how they try to like come up and be very clever. But it turns out an optimal strategy is that no matter what happens with the lights, they just always answer plus. They just show the plus papers. That is actually an optimal strategy. And they get the answer correct 3 times because they're correlated, but they'll fail on this other time and they'll be anti-correlated. And I can tell that they are not psychic, that they've just shared some hidden information. So this is the kind of intuition, this is the bound. If you have a hidden variable theory that's local, so it can't act faster than the speed of light, then this is kind of the limit for any kind of hidden variable theory. And Bell's theorem formalizes this over all possible hidden variables. So in our experiment, now we've got something that's a little bit different. We've got a, we're going to look what happens if instead of Alice and Bob sharing a hidden variable theory, they now share a entangled pair of particles. So I've got a source that shoots and gives Alice and Bob a whole bunch of these entangled pairs of particles. And now instead of a random number generator, I've got a, instead of these 2 lights, I've got a random number generator that tells Alice and Bob how to measure their particles, which basis. So I'm using photons, and we're going to use the polarization degree of freedom. And so the polarizer can be set to an angle A prime for Alice, B or B prime for Bob. And if they get a detection, that's a plus. They don't get a detection, that's a minus. And they can report the results back. So we can strictly do a mapping to this experiment. And we can play it with the quantum version of the game, where instead of a hidden variable theory, they now share entangled particles. If you do the math, it's a fairly easy exercise to go through, so I won't do it here. What you find is that with this version of the game, you can actually get a score of 2√2. So, you know, it's not quite the limit of 4, but it's definitely better than the limit of what you can get with a classical set of variables. Now, usually when I present this, somebody immediately says, wait, so does that mean you can use entanglement to send information faster than the speed of light? And I really like this XKCD. But the short answer is no, you cannot use this to communicate faster than the speed of light. You can't send information faster than the speed of light. Quantum mechanics is a non-signaling theory. And what's really going on here is that if we think about what it means to have a hidden variable theory, it means that you have determinism. You can exactly predict what's going on. And because you can't use these correlations to send information faster than the speed of light, it turns out that formally, those correlations have to be perfectly random. Even if you had complete knowledge about the system, you still couldn't predict how the correlations are going to behave. They have these stronger correlations, but you just don't know what your outcomes are going to be. Because if you did, you could turn that into a scheme for actually signaling or sending information faster than the speed of light. So that's Bell's theorem, and it is implied within it that you do have some kind of form of true randomness And that's going to be the engine that we're going to exploit to try and generate our random bits. So just briefly, I'm going to talk about one other thing, and that are these loopholes. And these are actually quite important, especially when you start considering this as a security type protocol, and you need to take this quite seriously. So there are 3 ways that Alice and Bob could have cheated my game. There's more than 3 ways, but there's 3 primary ways that they could have done it. So the first one is that I put Alice and Bob in separate rooms, but maybe I forgot to take away their cell phones and they could have just texted one another. So if I really wanted to ensure security, I need to move Alice and Bob very far apart and make them answer fast enough such that Alice just doesn't have time. Like when Alice's light goes off or she picks a setting is picked for her, she has to answer before any information about Bob's setting has a chance to reach her. So this is called our space-like separation. So we're going to use the fact that you can't send information fast at the speed of light and have them far separated. And that guarantees that Alice can't learn about Bob's setting before she has to answer, and vice versa. The second assumption is that Alice and Bob's random number generators have to be uncorrelated. So Alice can't just look at her pattern of lights firing and what her settings are, and then say, oh, I can see how that's correlated to Bob's setup, and then use that pattern of lights to predict what the next setting is. So you really do need to have good independent or uncorrelated sources of randomness picking those two settings. They don't have to be perfect randomness, they just have to be uncorrelated. The third thing that can happen is that whenever Alice gets the inner light go off, she can just refuse to answer. So she can just say, sorry, there was a technical malfunction. I didn't see what happened. I can't give an answer. And so that way they always win the game because they're only answering in cases when they should be perfectly correlated. And so if you do the math for a Bell test, it turns out that you have to have at least 2/3 of the times that you run the experiment, you have to have an answer given. And so this is something called the detector or the efficiency loophole. You have to have very good, the ability to capture all of your particles. So the problem was really it took us 50 years to simultaneously close all of these different loopholes. And there are many, many experiments going back to the very early 70s where we've done progressively better versions of these experiments. And for photons, you had these 2 very difficult competing conditions, which is you had to send the particles really far apart. But whenever you do that, you almost always incur a loss. And you have to detect the photons with this kind of high efficiency. So when I started, actually when I finished grad school and I was doing my postdoc, for a long time, the best commercial single photon detectors you could buy were rated around 60% efficiency. So already you just couldn't do the experiment with photons. And so it took me going to NIST to really be able to do this experiment, because Seiwu Nam, his group there, have developed the world's best single photon detectors. They're based on these superconducting thin wires that kind of meander in this sort of shape. And you run a current through these wires. You run them at about 700 millikelvin, so just about a degree above absolute zero. And if a photon hits this wire, with very high probability, it gets absorbed. And that action of it being absorbed heats up the wire in that little local spot, and it stops superconducting there. And then that causes the whole wire to stop superconducting, and you get this huge kinetic inductance that you can measure. And so recently, this past year, we've actually been able to get these detectors up to around 98% system detection efficiency. So that's the detectors are actually better than that, but we have losses in our fibers and other things that even getting the photons to them. So these are operating about as close as we can get to the theoretical limit. We're really close to that. So these detectors have been game-changing in quantum optics. So our experiment, the experiment I'll be talking about today, it was set up at NIST, and we have the source. It's basically almost like a right angle triangle. The source is at one corner. The top right-hand corner is where the lab was with the entangled source. And then we had a station in one end of the building at Alice, and then the other leg of the triangle, we had a Bob. This is not the optimal geometry. You really want to have things in a straight line so that you can have the maximum amount of time to operate, because you have all these very strict timing conditions for how things have to operate. But setting up the experiment, I realized that photons are a lot easier to deal with than people. It's not really treated very well when you walk to somebody's lab in the middle of the building and say, I need to kick you out of your lab so I could do this other experiment that's more important. And by the way, you also need to move out of this office and this office too. So these were literally the only spaces we had available in the building that could accommodate our correct geometry. And it made the experiment quite a bit more difficult and challenging, but we were able to set up in this kind of configuration. And so at the source, we were able to produce these polarization entangled photons. It turns out that when you don't have perfect efficiency, for the type of Bell inequality we're using, it's this causal horn, a technical note, you actually don't want to use a maximally entangled state. You want to use a biased entangled state. You can get away with less detector efficiency. You trade off in rates, but you can actually, you have a little bit more flexibility. And so our system at the time had about 75, 76% system detection efficiency. So we create a pair of photons in these kind of nonlinear crystals. There's a process called spontaneous parametric down conversion where a pump photon will fission spontaneously into a pair of entangled photons. We couple those into fiber. We send them, over 100 meters to Alice and Bob stations. We couple them out of fiber, and at the various stations, we have these Pockle cells that can switch a couple 100,000 times per second. And they rotate our measurement bases between these two different polarization angles. And so the photons pass through this, then we have to couple them back into fiber, and then we send them to our detectors. Our detectors at the time had about 90% efficiency. And so we can only lose, in this particular experiment, all that process of producing the photons, going through all these optics, coupling in, coupling out, coupling into fiber, and then being detected. If Alice detects a photon on her side, Bob has about a 76% chance of detecting his. And that was the thing that was really, really hard to do, and was kind of our great technical achievement for this. So we ran this experiment in 2015. I should just also mention, when you try to characterize, how far outside the light cone Alice is of Bob's measurement and vice versa, and you get all these Minkowski space-time diagrams, especially when you have this type of configuration, it gets very complicated. And so we wanted to be very, very paranoid. We wanted to take kind of the worst case scenario that we could possibly imagine, and then calculate some kind of confidence based on that for the space-time region. We spent some time thinking about it. So these green boxes, and you see the insets that kind of zoom in on the building, Alice and Bob, these regions represent the areas where I could move the source anywhere independently within its green box in the top right. Alice's setup, I could move anywhere within its green box, and Bob within his green box. And as long as all three stay within those green boxes, you're still space-like separated. So the worst case scenario that we're trying to guard against is that while we're running the experiment, maybe the security guards let in some extreme anti-quantum mechanics zealots into the building, and they take Alice's setup and they move it to the room next door, and they take the source and they move it outside the building, and they move Bob's source, into the hallway, into a whole other room. And even in those cases, we would still be satisfying the kind of constraints that we would need to close these kind of hidden variables, or to rule out these hidden variables. So we spent a lot of time trying to really go through and carefully characterize all of the timings and distances involved in the experiment. And so we did this experiment, and when you do the analysis, you have to use a hypothesis testing framework. And using that, we were able to measure a p-value, the probability that a local hidden variable theory, in some sense, just by chance, could have explained the results, was less than a part in 10 to the minus 9, which is much greater than 5 sigmas of equivalent Bell violation. So the analysis for how we close these loopholes, this was primarily done by Peter Bierhorst. And Peter, he was a postdoc who had came to work with Manny Nell at NIST. And Peter's now at UNO, and Peter is a phenomenal scientist, because when he joined the group, Peter did not believe, and I just see him, he's on the call right now, so I'm not going to slander you, but no, Peter is a really great scientist. He told me right off the bat, he said, this experiment is not going to work. He toured the lab. And then he did the analysis of the data, and he realized we violated the Bell's inequality. And he changed his mind. And he's been really instrumental in coming up with a lot of the kind of ideas for how to actually, capitalize and use these things. So, don't be afraid to change your mind. I think it's something we're lacking quite a bit in the world today. I also want to mention that when we were doing this experiment, both here and at NIST and over in Vienna, the data was taken the same week for both those experiments, as we've later found out that the LIGO, which I'm assuming a few of you at LSU may have heard of, got their experimental data too. So another kind of experiment, ours sort of contradicted Einstein's initial thoughts, and LIGO affirmed it. So a mixed week for Einstein, I'd say. So I want to just briefly mention, what do we mean by a p-value? Well, when you do this Bell experiment, you play that game, you get a score between 2 and 2√2, means you've got something entanglement based, or that's non-local. And maybe you measure a particular parameter. What a p-value is it's the area under the curve that says, what's the chance that a local hidden variable theory or local realism could have been by chance gotten the value that you observed or greater. And so it's just the area under the curve. And if you're careful, a certificate that tells you how much confidence you should have on the amount of randomness, that true randomness that had to be present in the correlations that you measured in order to violate the Bell inequality. And so you can turn that certificate, or you can turn that p-value into a type of certificate. And then there's classical ways which you can then extract that amount of randomness from your setup. And so this is a paper that came out of Nature a few years ago. Again, Peter Bierhorst led the theoretical effort on this. And we were able to produce 1,024 bits in about 10 minutes of data collection. And we certified the uniformity of these bits to a part in 10 to the 12. So that's a little bit complex. It'll take me a while to explain how uniformity works. But that's a very good certificate. And now we can do even better than that. We can do substantially better than that in less time with the latest versions of the setup. But to give you an idea of really what this means, the simplest test, the very first test you should do with the random number generator is to measure how much bias there is. Like, what's the discrepancy between the number of zeros and the number of ones? And that doesn't tell you if you're random or uniform, that just tells you how many zeros and ones are. But if you wanted to measure the bias in a random number generator, and your random number generator, to a part in 10 to the 12, well, that means that you have to measure some quantity with an error of the order of 10 to the part in 10 to the 12. Because you have normal statistics, you need to take, on average, 10 to the 24 bits. So that the square root of that is 10 to the 12. It's the square root of n squared. So you would need to run your random number generator long enough to capture.
Krister, I hate to interrupt you, but your connection's kind of getting a little bit messed up. So can I ask you to, is it possible to take off your mask, or?
I'm gonna hide here so no one can see me. Okay.
All right.
Is that better?
That's better. Yep.
So I was saying, if you wanted to measure a bias in a random number generator like this, then you would need to take 10 to the 24 bits to measure its accuracy apart in 10 to the 12. So if we think about how much 10 to the 24 bits is, if we go back to that new result from science that was generating, a couple hundred terahertz per second, terabits per second, they can't actually digitize and record all of that data. That's just their estimates from it. But let's just say that you had a really good random number generator that could run that fast. It would take several hundred years of running that thing full speed to just collect enough data just to measure the different distributions and zeros and ones. So suddenly, our 10 minutes of data to do this, and now we can get this down to around a minute, isn't quite so bad. And our current certificates are substantially better than this. And it's because we get to play a different game, which is the violation of the bound quality directly it tells us, as long as we're not sending information faster than the speed of light, which shouldn't be possible, it gives us a strong bound on a measure of how much randomness there is. So in my last few minutes, I want to just quickly mention some of our latest and greatest results. This experiment was actually a very costly way to generate randomness. We managed to produce 1,024 bits, but over the 10 minutes of running, Alice and Bob's random number generators consumed over 120 million bits. So we were getting one certified high quality bit out for every 117,000 bits we put in. And practically speaking, if you were to come and tell me, like, I want to build a good random number generator, well, what I would say is just take those random number generators and hash those 117,000 bits down. And that's way easier and a lot less work. And okay, you can't certify it, but it's going to give you a very good bit stream coming out. So there's a new technique, and again, this just came out. I'm not even sure if it's been published yet. It's online now in Nature Physics about randomness expansion. And what we're going to do is we're going to run our experiment in a different way, where instead of trying to do this certification check of the Bell test every single time on every trial, we're going to do it rather infrequently. And the inspiration is going to come a little bit from like food inspectors. So when you have a food inspector, they don't actually go through and test every single tomato or apple. What you do is you randomly spot check things to test. And so we're going to do the same thing. We're going to introduce a new party into our experiment called Spot. And Spot is going to tell Alice and Bob when it is they need to run their Bell test to try and do the certification, so we don't consume as many bits. And we don't know when that's going to happen, but the kind of we add Spot into the mix, and Spot is going to, in this particular case, consume 17 bits to figure out when to do the Bell test, and then Alice and Bob are going to consume 1 bit each. And when we run our experiment in this particular configuration, well, it takes us quite a bit longer. We had to run for about 120 hours. And then after taking 120 hours of experimental data, we actually kind of hit there's a very strict protocol that you have to put in place. We actually succeeded with our protocol. And at that point, you can see the red line here, that corresponds to how many bits we're consuming. And then how many bits the experiment generates. It takes a while. It takes almost 20 million of what we call these blocks. It's just you can convert that into a unit of time before we've actually built up enough confidence in those spot checks that we can even certify any randomness. And then we can start certifying more and more random bits. And at some point, when we stopped our experiment, we're actually able to produce about 24 more bits, certified bits, than we actually put into the setup. And in this particular setup, averaged over the whole run, we're producing about 3,600 bits per second. So that's quite a bit faster than the 1,024 bits in 10 minutes. It's just, it takes us a long time to get those, to be able to extract all of those bits. And so there's some really interesting things you can do to kind of build on this and for future directions. Right now, this experiment, again, it takes the size of a building, but we're working to try and shrink this down to the size of a chip so that everybody can have their own really secure source of what we call device-independent randomness that's based on these Bell tests that can actually be certified. So I want to leave you with one last thought, and that is, why does NIST care about entanglement and Bell test and whatnot? We do a lot of standards. Well, we have this project because we do a lot of cryptography. One of our projects is we have this randomness beacon that broadcasts at regular intervals every minute 512 bits of randomness. Now, you shouldn't use this for cryptographic applications, but there's a lot of applications where you have resource division, like lottery type things, like whose child goes to what school, who gets jury duty, those type of applications where you need a public source of trusted randomness. And we really wanted to think about what are the limits of randomness? Can you actually certify the quality of randomness? And that led us to the Bell test. And we're actually working, and this is what Elisa has been helping with this, is to hook up our great source of randomness in the lab and inject it into this beacon so it can become a public service. And so there's many applications of it. And the one that I think I'm maybe most excited about right now that we're actively working on is trying to use this to help combat, in some small way, gerrymandering. So with gerrymandering, if you let state officials draw up electoral boundaries, they do so in ways that give them unfair advantages. And there's some very famous examples of this. In fact, it gets so bad in some places, you can actually go download a font called Jerry, where the letters are made up of gerrymandered districts. Now, our hope is that instead of letting people draw the boundaries, why not let the beacon, through a secure protocol, draw up electoral districts that are constitutional and fair and really don't have any kind of partisan influence. And so we're working on a project to make this a reality. Now, I want to say that technology is not the underlying problem here. This is a fundamentally human problem that has led to us having this kind of gerrymandering in this very undemocratic way. And technology can't solve that. But in states like Colorado, we passed constitutional amendments that enforce now our state boundaries to be, or electoral districts to be drawn by a nonpartisan committee. And we're hoping to work with them to try and do this in a way that, if you can let quantum mechanics do this, then we can ensure that humans won't come in and tamper with that in the future. And so this isn't going to be the silver bullet, because that's a human problem of how do you actually overcome some undemocratic tendencies. But I do think we should be trying to do our best to contribute where we can. So I'm very excited about this and some of the otof applications that we've kind of coming down the line. So with that, I'd like to thank you for listening and leave you with the words of Alain Aspect, who did, I'd say, some of the most pivotal and influential of the early Bell test. And he said, "We must thank John Bell for having shown us that philosophical questions about the nature of reality could be translated into problems for physicists where naive experimentalists can contribute." And I really identify with the naive experimentalist side of things. So thank you. Thank you so much for listening.
Thank you so much, Dr. Krister Shalm, for that wonderful talk. We have time for questions if anyone has any. Yes, Dr. Wilder.
Do you have an anti-quantum zealot problem? Did you hear me? I can't hear the question at all, so maybe you could repeat it, Lisa.
Are you unmuted?
Oh, but I need to be able to hear me through the speaker, right? I'll come over here. Do you have an anti-quantum zealot problem? Still can't hear. I heard, do you have an anti-something, something, something?
Do you have an anti-quantum zealot problem at NIST?
No, but I get a lot of email from them and a lot of messages. Hanging up in my lab, or sorry, my office, which I'm not next to right now. I actually have a wall of letters and manuscripts and treatises that people have sent me. I call it our version of fan mail, where they're like, "You're wrong about this because I don't know anything about math, but I drew some cartoons and I think this proves entanglement." And so I've got a little collection of those. So.
John Dowling had the same thing. It's over here. You have something in common. Can you hear me? Okay. Yeah. All right. The next two questions are a little more serious. Well, the next one is not as serious. But you said that a psychic can win perfectly, but I don't know. You've probably seen this. Alice and Bob could share what's called the non-signaling distribution, and they could win with probability 1 with such a non-signaling distribution. And then one could contend whether that's really a psychic if you have a non-signaling distribution. Do you know what I'm talking about?
Is this is this also in ensuring like the non-locality constraints too?
It's this, okay, so it's a PR box, right? You've heard of a PR box. The thing is, the PR box, it's non-signaling, but it's not known how to realize it with quantum mechanics. I'm just being a little nitpicky.
Box is the psychic, yes. So in fact, that's how Peter constructed the proof, is you actually measure the amount of PR correlations in there. And the PR correlations, because they're non-signaling, but they can maximally violate it, you rewrite your distribution as some kind of, you can sort of think about it as a linear combination of this deterministic local hidden variable strategy, plus some amount of this perfect PR box. And the PR box, because it's non-signaling but perfectly correlated, has to be truly random. And then you rule out that new inequality, and that actually allows you to quantify, that's one way to quantify the amount of randomness that you can extract from these experiments. So yes, I mean, we're not sure if we actually, well, it would be really awesome if we did live in a PR box type universe. So like we'd have even stronger correlations, and you could build better computers, and I don't know, maybe we'd have world peace. But I'm not convinced we are living in that. But yes, it's still a very useful tool for trying to construct these proofs.
Okay. And I have a third question, and sorry to be hogging all the questions, but I'll pass the mic soon. So could you comment, I don't know if you might have commented on this in your talk, but could you comment on this point? In order to run the experiment, you need some randomness to begin with, to make the random choices of the lights that you had. So what you're doing all the time, is it a protocol for randomness expansion, or like, do you need a seed to get this going, or is there a way to make it work without a random seed to begin with?
Bootstrap up from something, and the Bell test, you need to have. So this is one of the things with any of these experiments. You already have to have a pretty good source of randomness in order to run your Bell test. But it doesn't have to be a fantastic source of randomness. And you can think about the vanilla version of the randomness or of device-independent randomness generation is taking some pretty good sources of randomness and turning them into certified sources of randomness.
Okay, so even if you were to start with pseudo-random numbers, could you then produce certified randomness? Oh, the volume's not.
No, I think you just stopped him in his tracks.
Okay. Did you hear me, Krister? Now we hear you. So I was asking about if you use pseudo-random numbers to begin with, could you produce from the experiment certified randomness?
Is that Alice and Bob's random number generators are uncorrelated from one another, and the entangled source.
Okay, but so you would need true randomness to get the process going, is that correct?
You can even have biased randomness, which I guess, depending on your definition, is random. You just need to have some source of inputs. I mean, it could be hashed phone book records. It doesn't really matter as long as Bob doesn't have access to Alice's her choices in advance, and the source doesn't have them either. So it's a way to take up, you know, it doesn't really matter. You don't want to have a terrible source of randomness because that's going to cause a lot of problems. It makes it much harder to actually certify. But what's really nice about the expansion is you can do this sort of thing about a snake eating its tail in some sense, where you can start with some seed randomness and get some certified randomness out, and then take that certified randomness and feed it into another Bell experiment as its inputs, and then get even more certified randomness out. And you can, starting from some small amount of seed, you can sort of generate almost like infinite amounts of randomness if you just keep cross-feeding things back in. There's protocols for how to do that. And we've been actually discussing about maybe there's some other challenges with this. Maybe there's another group that's also doing these similar types of experiments and actually doing a cross-feeding experiment across continents where their results feed into ours and ours feed into theirs, and then we just do several rounds to boost up. It's like a free energy Ponzi scheme, but except real and with, you know, because we're extracting entropy.
Yeah, very interesting. Thank you. Are there other questions?
Yeah. Hey, Lyndon, thanks for the talk. So could you, hopefully my voice is being heard. Could you comment very briefly on the uniformity measures that you're using for the random distribution of numbers that you're getting of 0 and 1s?
If you want to jump in on this, because you're probably even better positioned.
Yeah. So a perfectly uniform distribution, you know, has with an alphabet size of D, would have a probability of 1/d for each possible outcome. And so if something is within 10 to the minus 2 or 10 to the minus 12 of that uniform distribution, we measure that in terms of total variation distance, which means, you know, so we look at the distribution that we do have, and if you were to graph it out like bars, you know, little bars, and you were to measure the distance from each bar to the perfectly uniform height and add up all those little discrepancies, that if you added all of them up together, you would get 10 to the minus 12. That's the amount of distance in terms of probability from the distribution that's perfectly uniform, where everything equals 1/d.
I see. Okay, yeah, thanks for that, Peter.
And to comment on the pseudo-randomness, you know, I think that a little bit was lost with some of the sound issues. I believe in the Nature paper, we actually used pseudo-randomness to generate the settings, right, Krister? So I guess we do believe that we can generate true randomness from pseudo-randomness, because we believe that the pseudo-random process toggling the settings is independent in some ethereal sense from the systems being measured. Now, what does it mean for something that's technically not a random variable at all to be independent from something? That's, you know, a little bit of a head scratcher, but you know, I'm comfortable with that interpretation.
Thank you. Are there other questions?
All right, if there are any other questions, please ask now if you want to.
So, Krister, we wanted to chat with you afterwards if you have extra time. And maybe.
Oh, well, all right. Thank you, everyone, for attending this seminar. Thank you, Krister, for giving us your time, and this was a great talk. And just, all right, good afternoon and bye.
So, Krister, do you have a little extra time to chat? And for probably about another 15 or 20 minutes.
Yeah. Okay.
Over this desk. I have a hard time not standing